Good morning. Today we'll start with the flow over bodies, drag and lift. We consider flow of fluid inside pipes in the previous chapter, and we emphasis on the pressure drop and head loss and their relations to flow rate. In this chapter we consider flow of fluids over bodies that are immersed in a fluid called external flow, with emphasis on the resulting lift and drag forces. External flow is characterized by a freely growing boundary layer surrounded by an outer flow region that involves small velocity and temperature gradient. In internal flow, the entire flow field is dominated by viscous effects, while in external flow, the viscous effects are confined to a portion of the flow field such as boundary layer and wakes. When fluid moves over the body, it exerts pressure force normal to the surface and shear force parallel to the surface along the outer surface of the body. We are usually interested in the resultant of pressure and shear force acting on the body rather than the details or distribution of these forces along the entire surface of the body. So we start this chapter with discussion of drag lift, explore the concepts of pressure drag, friction drag and flow separation. We continue with drag coefficient of various 2-3 dimensional geometries. Introduction. Fluid flow over solid bodies frequently occurs in practice like the of plane and house and a wind. Trees, underwater pipelines, lift. The lift developed by airplane wings, upward draft of rain, snow, hail and dust particles in high wind, the transmission of red blood cells by the blood flow. These are examples of fluid flow over solid bodies. Therefore, developing a good understanding of external flow is important to the design of many engineering systems such as aircraft, automobiles, buildings, ships, submarines and all kinds of turbines. Sometimes a fluid moves over a stationary body and other times a body moves through a constant fluid such as a car moving through air. So these two seemingly different processes are equivalent to each other. What matters is the relative motion between the fluid and the body. Such motions are conveniently analyzed by fixing the coordinate system on the body and are referred to as flow over bodies or external flow. The aerodynamics aspects of different airplane wings designs, for example, are studied conveniently in the lab by placing wings in a wind tunnel and blowing the air over them by large fans. Also, the flow can be classified being steady and unsteady depending on the reference frame selected. The flow fields of geometries for most external flow problems are too complicated to be solved analytically, but with the help of computers and experiment data, it can be solved easily. So, the velocity of the fluid approaching a body is called free-storm velocity and is noted by V. It is noted by U infinity or U infinity when the flow is aligned with the x-axis. Since U is the used to denote the x component of velocity, the fluid velocity ranges from 0 at surface, no slip condition, to the free stream velocity at the away from the surface. The shape of body has profound influence on the flow over the body and the velocity field. The flow over a body is set to two-dimensional when the body is very long and constant cross section and the flow is normal to the body. The wind flowing over a long pipe perpendicular to its axis is an example of two-dimensional flow. Note that the velocity component in the x direction is 0 in this case and thus the velocity is two-dimensional. So this is a two-dimensional case. Now this is bullet axisymmetry case. The two-dimensional idealized approximation when the body is sufficiently long so that the end effects are negligible and approach flow is uniform. Another simplification occurs when the bodies possess rotational symmetry about the axis in the flow direction. The flow in this case is also two-dimensional and is said to be axisymmetric. In case of bullet, you can see there are two components, radial component and x component of the velocity. Second is the flow over the bodies can also be classified in compressible flow over automobiles, submarines and buildings, and compressible flows over high speed aircraft, rocket and missiles. Compressivity effects are negligible at low velocities when your Mach number is less than 0.3 and such flows can be treated as incompressible. Compressible flow involve partially immersed bodies with the free surface such as ship cruising in water and beyond the scope of this text. The body is also be defined blunt or streamlined on the basis of the shape. A body is said to be streamlined if the conscious effort is made to align its shape with the anticipated streamlines in the flow. Streamlined bodies such as race cars and airplanes appear to be contoured and sleek, while such as building tends to block the flow and is said to be blunt or bluff. Usually it is much easier to force a streamlined body through a fluid, and thus streamlined has been of great importance in design of vehicles and airplanes. Drag and lift. It is common experience that a body meets some resistance when it is forced to move through a fluid, especially a liquid. As you may have noticed, it is very difficult to walk in the water because of much greater resistance it offers to motion compared to air. Also, you may have seen high winds knocking the down tree, power lines and even trailer, and felt strong push the wind exerts on your body. You experience some feeling when you extend your arm out of window of a moving car. A fluid may exert force and moments on the body in the and about various directions. The force a flowing fluid exerts on a body in the flow direction is called drag. The drag force can be measured directly by simply attaching the body subjected to the fluid flow to a calibrated spring and measuring the displacement in the flow direction. Drag is usually an undesirable effect like friction, and we do our best to minimize it. Means by streamlining the body of the car, we can minimize the drag. But drag is somewhere beneficial, except like we try to maximize friction, for example, is a lifesaver in the brakes of automobiles. Likewise, it is a drag that makes it possible for people to parachute, for pollers to fly to distant locations, and for us to enjoy the waves of oceans and relaxing moments of leaves of trees. For two-dimensional flows, the resultant of the pressure and shear force can be split into two components. One in the direction of flow, which is the drag force FD, and another in the direction normal to the flow, which is FL, which is called lift. So for three-dimensional flows, there is also a side force component in the direction normal to the page that tends to move the body in that direction. The pressure and shear force acting on a differential area dA. So this is differential area dA, small area dA on the surface, and this pressure force on this is P into dA, and shear force is tau W into dA. The differential drag force and the lift force acting on a dA in two-dimensional flow are, this is your pressure force which will act normal to the surface, and this shear force which will act tangential to this surface. So in this case, drag force is equal to the component of this pressure force, which is the cos component, minus PdA cos theta, and the sine component of this shear stress, which will act in this direction. And what is lift for? The components of this PdA and this shear stress, which will act in vertical direction. So for the lift force in the vertical direction, this component will act minus PdA into sine theta minus tau W dA cos theta, where theta is the angle that the outer normal of dA makes with the positive flow direction. The total drag lift force acting on the body are determined by integrating these two equations. When you integrate this equation, this is the total drag force and this is total lift force for whole area. So above equations show both skin friction, wall shear and pressure in general contribute to the drag and lift. In the special case of a thin flat plate aligned parallel to the flow direction, the drag force depends on the wall shear only and is independent of pressure since theta is equal to 90 degree. When the flat plate is placed normal to the flow direction, however, the drag force depends on the pressure only and is independent of the wall shear, since the shear stress in this case act in the direction normal to the flow, that theta is equal to 0. This case, when your plate is normal to the direction of flow. Both lift and drag are strong function of angle of attack, as we discuss later in this chapter. The pressure difference between the top and bottom surface of wing generates a upward lift that tends to lift the wing and does the airplane to which it is connected. For slender bodies such as wings, the shear force acts nearly parallel to the flow direction and does it contributes the lift small. The drag force for such slender bodies is mostly due to the shear force, the skin friction. The drag and the lift force depends on the density of the fluid, the upstream velocity v, and the size and shape and orientation of the body, among other things. It is not practical to list these forces for a variety of stations. Instead, it is found convenient to work with appropriate dimensionless number that represents the drag and lift characteristics of the body. The numbers are drag coefficient CD and lift coefficient CL, and there drag coefficient is equal to CD is equal to force of drag divided by this, and lift coefficient is equal to force of lift divided by this. You can see this is the positive pressure at the bottom side and this is negative pressure, means pressure is less, which will cause a lift in the airplane wing. So pressure above and below atmosphere pressure are indicated by plus and minus sign. So this is pressure above atmosphere, this is pressure below atmosphere. Now in this case, area is the frontal area, the area projected on the plane normal to the direction of flow of the body. In other words, area is area that would be seen by person looking at the body from the direction of the approaching fluid. The frontal area of a cylinder of a diameter d and length L is equal to LD. In lift calculation of some things, thin bodies such as airfoil, area is taken to be planform area, which is area seen by person looking at the body from above in the direction normal to the body. Means in case of drag, we will take this frontal area of the body. In case of lift, we will take this area as which will be seen from the top of the body, this area. So drag and your this coefficient, your lift coefficient, drag coefficient depend on dynamic pressure and round number also, and they will also vary along the surface, but we are usually interested in the drag and lift coefficient for entire surface, so which can be determined by average the drag and lift coefficient. You can take the integral of a drag coefficient, lift coefficient. So this is the average drag coefficient, this is the average lift coefficient. So take example, when a body is dropped into atmosphere or a lake, it first accelerates under the influence of weight. The motion of body is resisted by the drag force. This is drag force which is acting from downward direction. So this continues until all the force balance each other and the net force acting on the body is zero. Then the velocity of the body remains constant during the rest of its fall if its properties of the fluid in the path of the fluid remain essentially constant. This is the maximum velocity of a falling body can attain, and it is called terminal velocity. The forces acting on a falling body are usually the drag force and the buoyancy force and the weight of the body. So this is your terminal velocity, when your weight of the body and your buoyancy force on the body will balance each other and the acceleration of body is zero. So this is the plate where your drag is only due to the skin friction. This is your plate which is perpendicular to the direction of flow, and in this case drag is due to the entirely due to the pressure drag, and here you have a cylinder in the flow. In this case the total drag coefficient is lowest for parallel plate, highest for vertical plate, and in between close to that of vertical plate for a cylinder. The part of the drag that is due to the wall shear stress is called skin friction drag, since it is caused by friction effects, and the part that is due to directly pressure is called pressure drag. So this is your drag coefficient for friction, this is drag coefficient for pressure, and when the friction and pressure drag coefficients of force are available, the total drag coefficient or a drag force can be determined by simply adding them. So this is your total drag coefficient, which is a part of friction, part of pressure, and this is total force which is due to friction and pressure both. Reducing drag by streamlining. The first thought comes into mind, how to reduce the drag by streamlining body. Even car sales people ask quick to point out the low drag coefficient of their cars owing to streamlining. But streamlining has the opposite effect on the pressure and friction drag. It decreases pressure drag by delaying boundary layer separation, and thus reducing the pressure difference between the front and back of the body, and increases the friction drag by increasing the surface area. The end result depends on the which effect dominates. Therefore, any optimization study to reduce the drag of the body must consider both effects and must attempt to minimize the sum of the two. The minimum total drag occurs at d by L is equal to 0.25 for the case shown below. So this is body here, where d is this thickness of this wing and L is the length of this body. So this is the velocity of the air in this direction. You can say this is a total drag which is a combination of friction drag and which is a combination of pressure drag, and sum of these two drag is minimum at this point, which correspond to d by L at 0.25. So we have to optimize between the two. Now this d by L will define the streamline of the body. If you increase the d by L further, that will result into the increase in the drag. The effect of streamline on a drag coefficient can be described by considering a long elliptical cylinder with different aspect ratio, length to thickness. Ratio L by D, where L is the length in the flow direction and D is the thickness. So this is your long elliptical cylinder, which L is the along the length flow direction and D is the your diameter of the cylinder. So in this case, in Z direction, cylinder is of B length. So in this case, frontal area is BD. This is your frontal area. Now this is your drag coefficient for L by D. You can see it is 1 when your L by D is equal to 1, means your cylinder is fully same L length and same D. It is fully cylindrical. So that time drag coefficient is 1. And when you approach to this side, you can see when your L by D ratio will decrease, and when you approach to at this point, it is almost increasing up to 2. As the aspect ratio is decreased, the cylinder resembles a flat plate and the drag coefficient increases to 1.9. The value for the flat plate normal to the flow. Note that the curve becomes nearly flat for aspect ratio greater than 4. You can also see when your aspect ratio L by D is greater than 4, the drag is minimum and curve is almost flat. So it means it is better to use L by D greater than this 4. The reduction in the drag coefficient at high aspect ratio is primarily due to the boundary layer staying attached to the surface longer and resulting pressure recovery. The friction drag on the elliptical cylinder with respect to ratio of 4 is negligible. Also you can see if viewer D approaches to the 0, L by D tends to infinity. So this is due to the frontal area which appears in the denominator of the definition of CD approaching 0. So it does not mean that the drag force increases drastically as the body becomes flat. You can also see if you go into this side, your drag will increase, but it does not mean your drag will increase drastically. This shows that the frontal area is inappropriate for the use in the drag force relations for slim bodies such as thin orbital and flatbeds. In such case, the drag coefficient is defined on the basis of the planform area, which is the perpendicular area to the direction of flow, which is simply the surface area for a flat plate parallel to the flow. This is quite appropriate since for slim bodies the drag is always entirely due to the friction drag, which is proportional to the surface area of the body. Flow separation, it is common safety measure to slow down the car on sharp turns, because at high speeds the tire, or you can say your vehicle, won't follow the curvature of the road and it will detach from the road. So in the same way, your water won't be able to follow the curvature of the geometry due to the sharp change in geometry. It will unfollow it and it will go into this direction. You can also see when there is sudden change in the pipe diameter, there is a flow separation. So water won't follow this profile due to sudden change. It will follow this profile. There is formation of eddies also at this place. The location of separation point depends on several factors such as round number, the surface roughness and level of fluctuation in the fluid stream, and it is usually difficult to predict exactly where separation will occur unless there are sharp corners or abrupt changes in the shape of the solid surface. But flow separation also occurs on a body which don't have a sudden change in, you can say, shape. This ball is gradually changing its shape. It's a round in shape, but still there is fluid separation. So when a fluid separates from a body, it forms a separator region between the body and the fluid stream. This low pressure region behind the body where recirculating and backflow occurs is called separator region. The larger the separator region, the larger the pressure drag. The effects of flow separation are felt far downstream in the form of reduced velocity. The region of flow trailing the body where the effects of the body on velocity are felt is called the wake. This region is called wake region. The separated region comes to an end when the two flow streams attach. At further downstream, these streams will attach. Therefore, the separated region is an enclosed volume, whereas the wake keeps growing behind the body until the fluid in the wake region regains its velocity, and the velocity profile becomes nearly flat, viscous, and rotational effects are the most significant in the boundary layer, the separated region and the wake. The occurrence of flow separation is not limited to blunt body. Complete separation over entire back surface may occur on streamlined body. In case of plane, you can see if the angle of attack, this is 5 degree, there is a lift force and drag force. If angle of attack increases to 15 degree, the lift force is this and drag force is this. But if you increase further angle of attack to 30 degree, you can see the lift fold will decrease drastically and the drag force will increase very drastically. So flow separation of the top surface of wing reduce lift drastically and may cause aircraft to stall. So the drag coefficient, it depends on the laminar and it also depends on the type of flow, if it is turbulent. Suppose the inertia effects are in low roll number called creeping flows and the fluid wraps around the body smoothly. The drag coefficient in this case is inversely proportional to the roll number. For a sphere, it is determined to be coefficient of drag is equal to 24 by roll number, where roll number less than 1. Then the drag force acting on the spherical object at roll numbers becomes drag. This is your drag force, which is coefficient of drag into multiply with this factor. This is 3 pi viscosity into V into D. This is which is known as Stokes law. You can also see this is drag coefficient in case of sphere when your roll number is less than 1, and this is drag coefficient in case of hemisphere. This is drag coefficient in case of circular disc, and this is drag coefficient in case of parallel disc, which is parallel to the fraction of the flow. Drag coefficient for various two-dimensional bodies for roll number greater than 10 raised to the power 4 based on frontal area, where B is the length in the direction normal to the page. So this is for square rod, this is for rectangular rod, this is round front edge, this is sharp corners, this is for circular rod or cylinder. For laminar as well as turbulent, this is for elliptical. For L by D ratio is given and corresponding laminar turbulent coefficient, drag coefficient is given. This is a drag coefficient for streamlined body. This is for parachute, which here drag coefficient is equal to 1.3. And this is for tree at various velocity, drag coefficient will change, will vary from this range. This is drag coefficient for bikes. And this is drag coefficient of car and passenger car depending on the shape of the body, and this is drag coefficient of building. Parallel flow over flat plates. So this is your flat plate and this is the free stream velocity. Here your boundary will start to form. Here your boundary thickness is 0, and when you go along the flow it will increase. So this region is called laminar boundary layer, where your flow is laminar, then it will go to transition and then flow become turbulent. Your turbulent boundary is further divided into 3 regions: your viscous layer, sublayer, then buffer layer, then overlap layer. For parallel over a flat plate, the pressure drag is 0, and thus the drag coefficient is equal to the frictional drag coefficient, or simply the friction coefficient, that is a CD, where CD is a friction, CF. Only this is due to friction. Once the average friction coefficient is available, the drag coefficient for force over the surface can be determined from. So FD is equal to FF equal to half CF area into density to V square. You can calculate the friction force on the plate. So this is the velocity profile in case of turbulent flow. In case of laminar it is more over parabolic, and it is in case of turbulent it is more over flat as compared to this flow. The roll number at x distance x from the leading edge can be expressed by this, where V is upstream velocity and x is the characteristic length of the geometry, which for flat plate is the length of the plate in the flow direction. Flow over a smooth flat plate, transition from laminar to turbulent above roll number 1 to 10 per 5, but does not become fully turbulent before the roll number reaches much higher values, typically around 3 to 10 power 6. In engineering analysis, the generally accepted value for critical roll number is 5 to 10 power 5. So this is a critical roll number where your flow will convert from laminar to transition. So this is called the value where your flow will become turbulent. So this is your local friction coefficient in case of flow over a flat plate. So it will first is maximum at the entrance and then it will decrease, and then at transition it will start to increase, and then further it is at maximum at the start of the turbulent flow, and then it again start to decrease. So we are more concerned to find the average friction coefficient, which is 1 by L integration of this local friction coefficient into dx. Also the boundary layer thickness, which is delta, can be found in case of laminar by this relation, and friction coefficient by this relation. And for turbulent flow you can use this relation to find thickness of boundary layer and friction coefficient. Now put this local friction coefficient in the both laminar turbulent in this equation. You will get here the total average friction coefficient for laminar and average friction coefficient for turbulent flow. Sometimes your flat plate is sufficient long for the flow to become turbulent, but long enough to describe the laminar flow region. In such case, the average friction coefficient is entire plate is determined by performing integral fully rough turbulent regime. This is the your friction coefficient, where E is the surface roughness and L is the length of the plate in the flow direction. In the absence of better one, this relation can be used for turbulent flow on the rough surface when round number is greater than 10^6, especially when this ratio is greater than 10^-4. Friction coefficient for parallel flow over smooth and rough plates are plotted in the figure, both laminar and turbulent. Note that friction factor increases severalfold with the roughness in turbulent flow. Also, note that the CF is independent of round number in fully rough region. So if Ly, this roughness ratio is large, it means this is smooth pipe. If this Ly roughness ratio is less, it means this is rough pipe. So this dotted line and this side, it represents the rough pipe. So in the rough pipe, you can see your friction coefficient is constant for parallel flow over smooth and rough plate. The reason is that it is independent and you can see it is constant. But below this, you can see it will first decrease, then it will increase. And this is for laminar and this is for turbulent, and this is in between you have a transition. Flow over cylinders and spheres. Flow over cylinders and spheres is frequently encountered in practice. For example, tube in a shell and tube exchanger involve both internal flow through the tubes and external flow over the tubes, and both flows must be considered in analysis of heat exchanger. Also, many sports such as soccer, tennis and golf involve flow over spherical walls. The characteristic length for a circular cylinder or sphere is taken to be the external diameter d. Thus, the Reynolds number is defined as Vd upon V, where V is uniform velocity of the fluid as it approaches the cylinder or sphere. The critical Reynolds number for flow across a circular cylinder or sphere is about 2 into 10^5. That is, the boundary layer remains laminar for number less than 2 into 10^5 and becomes turbulent for number greater than 2 into 10^5. Cross flow over a cylinder exhibits complex flow pattern as shown in figure. So this is your circular cylinder at round number 2000. You can see this is laminar boundary layer separation at this point, and this is your wake at the back side. The fluid particles on the mid plane strike the cylinder at stagnation point, bringing the fluid to a complete stop and thus raising the pressure at that point. This point is your stagnation point here. The pressure decreases in the flow direction while the fluid velocity increases. At very low upstream velocity, not less than 1, the fluid completely wraps around the cylinder and 2 arms of the fluid meet on the rear side of the cylinder in an orderly manner. So where roll number is very less 1, this flow is like this, and these 2 layers will meet at the back side. So in this case, there is no wake at the rear end of the cylinder. The nature of the flow across a cylinder or sphere strongly affects the total drag coefficient CD. Both the friction drag and pressure drag can be significant. The high pressure in the vicinity of stagnation point and low pressure on the opposite side in the wake produce a net force on the body in the direction of flow. The drag force is primarily due to friction drag at low Reynolds number, when Reynolds number is less than 10, and to a pressure drag at a high Reynolds number. Both factors are significant and intermediate Reynolds number. So this is when your Reynolds number is 1, and this is Reynolds number will increase. You can see coefficient of drag, it will decrease along with the increase in Reynolds number. This is for smooth cylinder and this is for sphere. At about Reynolds number 10, separation starts occurring on the rear of the body with the vortex shedding. At about Reynolds number 90, the region of separation increases with increasing Reynolds number up to about Reynolds number 10^3. At this point, the drag is mostly about 90% due to pressure drag. The drag coefficient continues to decrease with increasing Reynolds number in this range. A decrease in the drag coefficient does not necessarily indicate a decrease in drag. The drag force is proportional to the scale of the velocity, and increase in the velocity at higher Reynolds number. Flow separation occurs at about 80 degree measured from the front stagnation point of cylinder. This is stagnation point, and you can see 80 degree there is flow separation. When the boundary layer is laminar and about theta is equal to 140. So in case of when it is turbulent, the delay of separation in turbulent flow is caused by the rapid fluctuation of the fluid in transverse direction, which enables the turbulent boundary layer to travel further along the surface before separation occurs, resulting in narrower wake. So here wake is narrower as compared to this. Keep in mind that turbulent flow has a fuller velocity profile as compared to the laminar case, and thus it requires a stronger adverse pressure gradient to overcome the additional momentum close to the wall. Lift was defined earlier as component of net force due to viscous and pressure force. That is, a pressure perpendicular to the flow direction, and the lift coefficient was expressed as CL is equal to FL by half density V square A. This force is called lift force, which is perpendicular to the shape. Now in this case, area in this case is normally the planform area, which is the area that would be seen by person looking at the body from above in the direction normal to the body, and V is upstream velocity. So this planform area is B into C. This is B span of the wing, and your C is the chord length of the wing. The average lift per unit platform area F by AL, A is called the wingspan loading, which is simply the ratio of the weight of the aircraft to the planform area of the wings, since lift equals to the weight during flying at constant altitude. The pressure change in the flow direction along the surface, but it remains essentially constant through the boundary layer in the direction normal to the surface. Therefore, it seems reasonable to ignore the very thin boundary layer of the airfoil and calculate the pressure distribution around the airfoil from literally simple potential flow theory, zero vorticity, irritation flow, for which net viscous forces are zero for flow past an airfoil. The flow field obtained from such calculation are sketched in this figure. You can see this is the irritation flow past the symmetrical airfoil, zero lift. So our angle of attack is zero. So the pressure at the upper side and lower side is same. So there is net pressure difference is zero. So there is no lift in this irritation flow past the symmetrical airfoil. There is zero lift. For the non-symmetrical airfoil, which is at a small angle of attack, the front stagnation point has moved down below the leading edge. You can see this point has moved down below the leading edge for non-symmetrical airfoil. The rear stagnation point has moved upward at this point. But surprisingly, the lift produced is calculated again to be zero, a clear contradiction of experimental observation and measurement. But their lift is zero in this case. So it means we have to modify our equations to bring it in line with the observed phenomena. You can also see here in this case, this flow has to make a U-turn, and which is in actual case is not possible. Even if you take the example of a car, it is impossible to take a sharp U-turn at such a high velocity. So this is not possible. So means the stagnation point will move backward and it will come back to this point. So this is the actual flow past a non-symmetric airfoil, and it will produce a positive release. Means this point will move backward and it will come at this position. This way the two flow streams from the top and the bottom sides of the airfoil meet the trailing edge, yielding a smooth flow downstream parallel to the trailing edge. Lift is generated because the flow velocity at the top surface is higher, and thus the pressure on the surface is lower due to the Bernoulli's effect. You can see this fluid has to take a longer path, so it has to cover the longer path. So the velocity of this air is increasing at this point, and while velocity of fluid is low at this point, so which will make a pressure difference between the lower point and upper point, which will result into the lift of this wing. And net vertical force on the wing in the vertical upward direction. So you can see if you increase the angle of attack, which is this alpha. So this is the direction of air, and this is the angle of the wing with the stream velocity of air. This is alpha. If you increase this angle of attack, suddenly a counterclockwise starting vortex is shed from the airfoil, while clockwise circulation appears around the airfoil, causing lift to be generated. So this is counterclockwise circulation, and when you lift the wing, it is clockwise circulation. The potential flow theory and observed phenomena can be reconciled as follows. Flow starts out as prescribed by theory when with no lift, but the lower fluid stream separates at the trailing edge when the velocity reaches a certain value. The force that separated upper fluid stream to close in at the trailing edge, initiating clockwise circulation around the airfoil. This clockwise circulation increases the velocity of the upper stream while decreasing that of lower stream, causing a lift. So upper stream velocity will increase, it has to travel a longer path. Lower stream velocity is less, it has to travel a lesser path. So which will cause a lift into the vertical direction. A starting vortex of opposite sign, counterclockwise circulation, is then shed downstream. You can see this is your counterclockwise circulation vortex. When the potential flow theory is modified by addition of an appropriate amount of circulation to the move the stagnation point down to the trailing edge, excellent agreement between theory and experiment for both flow field and the lift. It is desirable for airfoils to generate the most lift while producing the least drag. Therefore, a measure of performance of airfoil is to lift to drag ratio. So this is the measure of performance. If lift to drag ratio is higher, it means it is better. So this is the angle of alpha, angle of the flap. You can say when it is 0, this still there is a CL by CD ratio up to this value. And as if you increase the alpha into up to here, up to 6 degree, your CYLD ratio will increase, and then if further increase will cause a stall into the CL by CD ratio. You can say your lift to drag coefficient can be of the order of 100 at this point. So this is a particular Nodal number. One obvious way to change the lift and drag characteristics of airfoil is to change the angle of attack. Means by changing the angle of attack, you can change this ratio on an airfoil. For example, the entire plane is pitched up to increase lift since the wings are fixed related to the fuselage. Another approach is to change the shape of the airfoil by use of movable leading edge and trailing edge flaps, as is commonly done in modern large aircrafts. You can see during takeoff, drag is for lesser time, takeoff is least time, and the cruising is the most of time airplane will fly. So during takeoff, you can increase the wingspan, you can increase the wings, and during cruising, you can decrease the size of wing to decrease the drag. So the flaps are used to alter the shape of wings during takeoff and landing to maximize lift and to enable the aircraft to land or take off at low speeds. The increase in drag during this takeoff and landing is not much of concern because the little short time period involved. Once at cruising altitude, the flaps are retarded and the wing is returned to its normal shape with minimum drag coefficient and adequate lift coefficient to minimize fuel consumption while cruising at a constant altitude. Note that even a small lift coefficient can generate a large lift force during normal operation because of the large cruising velocities of aircraft and proportional to the lift to the square of the flow velocity. Lift coefficient can also increase from about 1.5 for airfoil with no flaps to 3.5 for double slotted flap case. You can see this is clean with no flap, this is slotted flap, and this is double slotted flap. So lift is increased from 1.5 to 3.48 by using double slotted flap. You can also see in case of double slotted, drag coefficient is up to 0.3 as compared to clean flap, drag coefficient is less. So this is 5-fold increase the drag coefficient, and the engines must work much harder to provide the necessary thrust to overcome this drag. So in this case, engine has to do more work. The angle of attack of flaps can be increased to maximize the lift coefficient. Also, the leading and trailing edge extend the chord length and thus enlarge the wing area also. The minimum flight velocity can be determined from the requirement that total weight of aircraft to be lift is equal to CL is equal to CL maximum. That is, weight of aircraft is equal to force, lift force, and it is equal to this. Now from here you can find the minimum velocity which is required. Now this is the question. For a given weight, if weight of aircraft is given, the landing or takeoff speed can be minimized by maximizing the product of this lift coefficient and area. One way of doing is to use flaps as already discussed. Another way is to control the boundary layer, which can be accomplished simply by simply by leaving flow sections between the flaps. You can say slots. Means if in the wing, if you produce a slot, it will minimize this overall product of this quantity. This is done by allowing air to move from the high pressure region under the wing into the low pressure region at the top surface. Note the lift coefficient reached its maximum value, CL is equal to CL maximum, and thus the flight velocity reached its minimum at the stall conditions, which is a region of unstable operation and must be avoided. Means we have to be above this minimum velocity. So the federal aviation administrator does not allow operation below 1.2 times the stall speed for safety reason. End effects of wing tips for airplane wings and other airfoils of finite size. The end effects at the tips become important because of fluid leakage between the lower and upper surfaces. The pressure difference between lower surface high pressure region and the upper surface low pressure region drives the fluid at the tips upward, while the fluid is kept toward the back because of relative motion between the fluid and the wing. So this results in swirling motion and spirals along the flow called the tip vortex. So this you can see a tip vortex here and this tip vortex here. So this is trailing vortices from a rectangular wing with vortex cores leaving the trailing edge at tips. So the result in this swirling motion. So at the tips of both wings, vortices are also formed along the airfoil between the tips of the wings. These distributed vortices collect toward the edge after being shed from the trailing edge of the wings and combine with the tip vortices to form two streaks of powerful trailing vortices along the tips of the wing. So this is, you can say, tip vortices produced by the tip of wings of this plane. The trailing vortex is generated by large aircraft continues to exit for a long time for long distance over 10 km before they gradually disappear due to viscous dissipation. Such vortices and the accompanying downdraft are strong enough to cause a small aircraft to lose control and flap over it. It flies through the wake of the large aircraft. Therefore, following a large aircraft closely within 10 km poses a real danger for small aircraft. This issue is the controlling factor that governs the spacing of aircraft at takeoff, which limits the flight capacity at airports. In nature, this factor can be used to advantages by birds that migrate in V formation by utilizing the updraft generated by the bird in front. It has been determined that the bird in a typical flock can fly to their destination in V formation. Also, military jets are also occasionally fly in V formation. The ratio of square of average span of an airfoil to planform area is called aspect ratio. For an airfoil with a rectangular planform of chord C and span B is expressed as, so aspect ratio is equal to B square by BC is equal to B by C. Therefore, the aspect ratio is a measure of how narrow an airfoil is in the flow direction. The lift coefficient of wings in general increase while the drag coefficient decreases with increasing aspect ratio. This is because a long narrow wing, large aspect ratio, has a shorter tip length and thus smaller tip losses and smaller induced drag than a short and wide wing of the same planform area. Therefore, bodies with large aspect ratio fly more efficiently, but they are less maneuverable because of their large moment of inertia. Body with smaller aspect ratio maneuver better since the wings are closer to the central part. So it is no surprise that fighter planes and fighter birds like falcons have short and wide wings, while large commercial planes have long and narrow wings. The end effects can be minimized by attaching end plates or winglets. This is your winglet here at the tip of the wings perpendicular to the top surface. The end plates function by blocking some of the leakage around the wing tips, which result in considerable reduction in the strength of tip vortices and induced drag. So wing tip feathers on birds fan out for the same purpose. You can see this is our wing tips here. The lift coefficient increases almost linearly with the angle of attack alpha. You can see here, if you increase the angle of attack alpha, your lift coefficient will increase. So this is for two different wings are given. So this is for non-symmetrical and this is for symmetrical airfoil. The drag coefficient also increases with the angle of attack, often exponentially. Therefore, large angle of attack should be used for short periods of time for fuel efficiency. You can see as the angle of attack increase, your drag also increase. lift generated by spinning. You have probably experienced giving a spin to tennis ball, or we are also spinning golf and saucer ball. The player utilize spin, and this spin will lift the ball to go at longer distance. The phenomenon of producing lift by rotating of a solid body is called Magnus effect. So you can see here cylinder. When your cylinder start to rotate, so this is stagnation point. When your cylinder is still stationary, and it will start to rotate, it will shift the stagnation point below here, and which result into the lift. So this is high velocity, low pressure, and this is low velocity, high pressure. You can see the stagnation point shifts down, and the flow is no longer symmetric about the horizontal plane and passes through the center of cylinder. The average horizontal, you can say average pressure on the upper half is less than the average pressure at the lower half because of Bernoulli's effect, and thus there is a net upward lift acting on the cylinder. The similar arrangement can be given for lift generated by spinning ball.